Okay, grade 12s, this is our fifth and final time trying to get this to go. What I would like you to do is, if you didn't watch the video on the website, please go back and watch it now. It'll help explain what a calorimeter is. First, we're going to look at, so we're going to quickly revisit that. Calorimeter is an object that allows us to measure the heat of a reaction based on the effect it has on the substance around it, which in 99% of the case is water. Then we can use Q equals mc delta T to determine the energy that was created by the reaction, because we can monitor the temperature change. We can use the first law of thermodynamics to justify this, because what we know is that energy is neither created nor destroyed, it just transfers forms. So the energy absorbed or released by the reaction will transfer to the water, and it will be the same amount of energy that is used to increase the temperature or decrease the temperature, depending on whether it's an exothermic or an endothermic reaction. So this would be an that would be an endo. And if the water absorbs and increases in temperature, it's an exothermic. So let's look at how we would actually do this in a question. You're going to get a how-to sheet tomorrow. The one thing that we want to point out, and that's crucial for you to understand, is the definitions of the heat of combustion, formation, solution, etc., that is the amount of heat absorbed or released when 1 mole of a substance is combusted or formed or dissolved or neutralized. This will look like delta H and then either combustion, solution, versus stoichiometric relationship, which will be delta HR. The other thing we want to see is that we're going to create two columns, one about our reactants, one about our surroundings. First example we're going to look at. 2 grams of magnesium is burned in a vessel immersed in 100 grams of water. The temperature increases by 1.5 degrees Celsius. Determine the heat of reaction of magnesium. Let's look what we've got. We've got 2 grams of magnesium, and we want to find the heat of reaction of magnesium. Just like on Wednesday, heat of reaction always involves a stoichiometric relationship. The other thing we need to look at is that we've got 100 grams of water, and that water increase in temperature by 1.5 degrees Celsius. So we've got our reactants, which in this case is magnesium, and we've got our surroundings, which will always be water. And it says that the Q, in this case, the heat released by magnesium, will be equal to the energy absorbed by the water. We always know that to measure the heat absorbed or released by water, we can use Q equals mc delta T. In this case, our mass is 100 grams. That's from the question. Our C is our specific heat capacity, 4.18 joules per gram degree Celsius. That's a value that you're responsible for knowing. And our temperature chain is 1.5 degrees Celsius. So in this case, we can actually calculate our Q. And whenever you're asked for the heat of reaction, you should be able to calculate Q for your surroundings. In this case, it equals 627 joules. Let's go over here. We have a mass of 2 grams, and we're asked for the heat of reaction. Oh, heat of reaction, stoic. So what we do now is we don't need to do anything else in terms of the surroundings, but what we do need to do for the reactants is write out a balanced chemical equation for the combustion of magnesium. So magnesium plus oxygen always travels as a diatomic, produces a magnesium oxide. And then there's our heat of reaction. We need to balance our chemical equation. Now, we know that in this reaction, we have 627 joules. this is our question mark. Oh look, I have a hair appointment tomorrow. And we know that we have a mass of 2 grams. We need to set up a mole energy ratio just like we did last Wednesday. So molar mass is 24 grams. Our moles is equal to mass over molar mass. So in this case, it's 0.083. Set up a mole. So we have 0.083 producing 627 joules of energy. We want to find out what 2 grams will produce in this heat of reaction. So we use our cross multiplication. Delta HR is equal to, well, let's figure it out. 15,108.4 joules. So the heat of reaction for magnesium in this balanced stoichiometric relationship, heat of reaction is always about a particular reaction, is 15,108.4 joules. On the contrary, if we go to a question like this, well, so I'll just reactants, surroundings. We have got a 5-gram sample of sodium, 75 grams of water, that's our surrounding, 30-degree temperature change, and it wants to know the heat of combustion. Here's where that definition comes in. The heat of combustion is for 1 mole of sodium. It doesn't matter the reaction, it's for 1 mole of sodium. So let's list our variables. 5 grams. For our heat of combustion is our question mark. That's what we're trying to find. Our mass of our surroundings is 75 grams. Our specific heat capacity, as always, is 4.18 joules per degree Celsius. Our change in temperature is 30 degrees Celsius. First law of thermodynamics says the Q released by the sodium will equal the Q absorbed by the water. We can find the Q of the water using Q equals mc delta T. So when we do the information here, what we'll find is that there's 9,405 joules of energy released when 5 grams of water are reacted. Now we need to set up a mole energy ratio. On the top, I want you to put what happened in the calorimeter. And on the bottom, we're going to put in our heat of combustion or solution or formation, whatever we're putting in here. So this will always be 1. We need to take the value of the moles of what was reacted. This is our reactant side. And then we know that 1 mole, our heat of combustion, that's what we're looking for right here. We can find a value here. It is 0.217. 0.217 mass divided by molar mass. And we took this and put it here. Cross multiplication, and you will find that the heat of combustion of sodium is equal to 43,263 joules. If you would like to try one more question with me, by all means go ahead. Otherwise, I will see you Tuesday in class. Please watch the video prior to this. You should have some examples written down so you have something to go back to. All right. For those of you that stuck around, try this question first. We've got 15 grams of calcium. Here's our reactant. We combust it in a calorimeter. How much will the temperature be raised in a vessel? So this is talking about water. So this is our surroundings in a vessel with 100 grams of water if the heat of combustion of calcium is 23,000 joules. All right, pause the video, give it a try. Make sure you set up your 2 columns and put the information on. Try it, and then give it a play and see how you did. Okay, welcome back. So let's list our variables. Mass. Because we're dealing with heat of combustion, this is going to be per 1 mole. So we know that we're going to have to set up a mole energy ratio. Let's put, we have 100 grams of water. We want to know what the change in temperature will be, so that's our question mark. Heat capacity for water always stays the same. We can't calculate Q at this point, so we're going to have to find that. That's what we're going to have to look for in our mole ratio. Last but not least, we are given the heat of combustion of calcium, which is 23,000 joules per mole. So we said heat of the delta H is always on the bottom, calorimeter is on the top, 1 mole for heat of combustion, and it told us our value this time, so we can just plug that in. We can calculate the moles that we'll plug in over here. So 15 divided by 40 will give us 0.375 mass divided by molar mass. If we use cross multiplication to find out our Q value, it is 8,625. Okay, then we isolate our unknown, and in this case, our delta T See you on Tuesday. Happy Thanksgiving.